Thanks, everyone. Thanks for giving up lunch or whatever you're giving up to be here. I am just going to start by introducing you to this fellow. The book is sort of arranged with 13 species as their sort of focal point. And this guy's at the end, so I'm giving away the end of the book, but it's not really, it doesn't really have a surprise ending, so I think I can do that. So he's a Hawaiian crow or an alala, and there used to be several species of Hawaiian crows, so they're sort of like, which probably diverged from like the crows you see around New York, probably several 100,000 years ago. So it's a case a bit like Darwin's finches, where a very small founder population arrived on the Hawaiian archipelago. We don't know how, because Hawaii is really quite distant from the mainland. Thousands of miles, and then they speciated, radiated out so that they could occupy the different islands and fill different ecological niches. But the difference is that actually most of the species of Hawaiian crows went extinct before modern times. And this one is also under very heavy threat, and in the 80s, the state of Hawaii realized that there were only very few left. They took them into captivity to try to breed them. Oh, thanks. No, I'm good. Thanks a lot. And this particular bird is a male bird by the name of Kanoe. And he was born at this breeding center, which is actually on Maui. The bird is native to the Big Island, but this breeding center is on Maui. And he's a very odd duck, as they say. He doesn't really think of himself as a crow. He seems to... We're not sure what he self-identifies as. One woman who takes care of him told me that he once fell in love with a spoonbill. So he refused to mate with any of the females. At the Maui facility, there's maybe 50 females, 100 birds altogether, and he refused to mate with any of them. But his genes are really important, so they took him to the veterinary hospital at the San Diego Zoo. And there he came under the care of a very experienced reproductive physiologist who was really eager to get a vial, let's just put it this way, of his genetic material to take back to Maui with her. So every spring, when it's breeding season on Maui, she takes Kanoe on her lap and strokes him in a way that male crows are supposed to find very exciting. Hoping that he's going to deliver so that she can take a vial of his ejaculate back to Maui. But at the time I visited, he had not yet delivered, so she was still at it. And crows are really smart, as you know, and Kanoe can imitate human speech, and he says, "I know." That's his phrase, which is really quite extraordinary. And when I heard that, it sounds kind of demented. He has this demented sound. But it seemed to really encapsulate a lot of the themes of the book. On the one hand, the incredible lengths that people are going to try to save this species. Meanwhile, though, all of the forces that brought the Hawaiian crows to this point are all still raging, and in fact are being increased, because Hawaii, there's now avian malaria on Hawaii. There didn't used to be mosquitoes. Now there are mosquitoes with avian malaria, and as the climate warms, these mosquitoes are moving up the mountain slopes. So there used to be sort of refuges for some of the native birds on the tops of Hawaii's very tall mountains, and avian malaria is now moving up the mountains. So birds on Hawaii are really in trouble. So he is sort of the emblem, in a way, for the whole book. And he's the animal that I end it with. So I guess I'll sort of step back and say, what is the book? What is the sixth extinction? The implication here, obviously, is that there are 5 other extinction events, and that is true. These are what are called the Big Five, the major mass extinctions of the last 500 million years. And what you're looking at is time is running from your left to your right in millions of years, so 600 million years ago to today. And where you see those dips, you're seeing the number of marine families. This is from the marine fossil record, and you're seeing the number of marine families on the y-axis. And if you remember from intro bio, a family is a level right above a genus, so species, genus, family. And if even one species made it through this extinction event, then the species is considered a survivor. So on the species level, the losses were much, much greater than they are even on the family level. And mass extinctions are just defined as moments in time when the diversity of life suddenly and very radically contracts. One British paleontologist, Michael Benton, whom I quote in the book, uses the metaphor of the tree of life. During a mass extinction, he's written, vast swaths of the tree are cut short as if attacked by a crazed, axe-wielding madman. So the first number one there, that's occurred about 440 million years ago at the end of the Ordovician period, when most of life was still in the sea. So that was very devastating to marine organisms, but not to terrestrial organisms because there just were no terrestrial organisms. And number 5, that's the most famous, most popular, if you will, and that is the extinction event that did in the dinosaurs and a lot of other groups at the end of the Cretaceous period. And there's a pretty broad scientific consensus that that was caused by an asteroid impact. I don't have a photo I can show you, but this is someone's best guess of what that looked like. So to say we're in the middle or on the verge, some people would say we're on the verge, some people would say we're already pretty deep into. The 6th extinction is obviously a pretty serious claim. And this claim arises from the fact that we are changing the world very radically and very, very fast, so not unlike an asteroid impact. And in fact, I have heard scientists say that right now we are the asteroid. So how are we doing this? There are a lot of ways. I'm just going to touch on a couple today. We're changing the atmosphere. You all know this. It's really simple stuff. We drive our cars. We light our homes. And all of this we're doing with fossil fuels right now. And there's 7.2 billion of us on the planet, so it adds up pretty quickly. And what we're doing when we are burning fossil fuels is we're taking carbon that's been buried underground over hundreds of millions of years, and we're shooting it back into the atmosphere very, very quickly, in a matter of centuries, quite possibly. So we're basically running geological history backward and at a very, very high speed. And if you were an alien and you came to Earth, you could actually easily conclude, that what we're doing, that the whole point of modern industrialized society is actually to effect this transfer as quickly as possible, to see, how much carbon we can get out of the ground and how fast we can throw it back up into the air. And if the aliens were measuring this process, they'd say we're actually, doing it pretty good. We're doing it as well as we possibly can. We're increasing CO2 levels every year. These are obviously our measurements of this process. I'm sure you're all familiar with this graph. This is the Keeling curve, measuring CO2 concentrations in the air, once again from Hawaii, from the National Weather Services Observatory on Mauna Loa. And that jig-jag pattern, that seesaw pattern you see, that's a seasonal signal, because when the trees and plants of the northern hemisphere put out their leaves for photosynthesis in the summer, global CO2 levels fall, and when they drop their leaves in the winter, then they rise again. So that's quite a recent reading, 396 parts per million. You may recently have read that CO2 levels hit 400 parts per million. They did very briefly at the end of last winter. They're going to again now, this winter, and then they're going to keep rising in that seesaw sort of way until they never go below 400 parts per million, because obviously, we show no signs of ceasing to emit CO2. And if we want to see how we're doing on a longer term way, then we can look back at ice cores. Probably many of you have seen this graph too. What you're looking at here, once again, we have parts per million of CO2 on the y-axis, time on the x-axis, running once again from left to right. So from 800,000 years ago to the present, you're looking at actual bubbles of past atmospheres that were extracted from an ice core taken on Antarctica. And all that the Antarctic ice sheet is just layers of snow that were laid down year after year. So we can actually see over time what happened to the atmosphere. And those jig-jag cycles that you see, those are ice ages. Okay, so when CO2 levels are low, ice creeps down all the way to the island of Manhattan, which was glaciated in the last ice age, and then it creeps back up again into the Arctic. And you're looking at 8 glacial cycles there. You see where people emerged around 200,000 years ago, and you can see that CO2 levels were never above 300 parts per million over the last 800,000 years until very, very recently. And now we're going up at what looks, on a scale like this, to be a vertical line. And if we want to go even further back, we can tease out the composition of past atmospheres by looking at things like the shells of little tiny marine creatures that fell to the bottom of the sea. And those have big error bars. But it seems pretty clear that to get CO2 levels that are significantly higher than today's, you have to go back to around the Miocene, around 20 million years ago. And at the rate we're going, we could reach those levels by the middle of this century. And if we keep on going, we could reach levels probably not seen since the Eocene, around 50 million years ago, by the end of this century. So obviously, what's significant about this is, on the one hand, CO2 is just a greenhouse gas. I'm not going to bore you, with the global warming spiel because you all know it. But I am going to just show you this little video that NASA has made. It's just a recreation of global temperatures over the last 130 years or so. And what you need to know to understand it is that as the colors get warmer, so more orangey and more yellow, the world is warming. That signifies warmer temperatures. So here we go. So that stops in 2011, but so hopefully they'll update it soon because it's a very sort of powerful visual representation. And so what does that mean for living things, for the creatures on this planet? The polar bear has sort of become the icon of species that are endangered by climate change because the sea ice, the Arctic sea ice, is disappearing very, very fast. And without minimizing the problems that the polar bears are facing, what I write about in the book actually is that it's actually likely that climate change is going to have a even more profound effect in the tropics. And there are a couple of reasons for this, one of which is just that the tropics are where most things actually live. So in this slide, you're looking down from about 12,000 feet. We're in the Andes in Peru. You're looking down that ridge. And I went there with a scientist from Wake Forest who had laid out these tree plots. And each plot was about 2.5 acres, was exactly 2.5 acres. And there were about 20 of them arrayed down this ridge so that each one had a different elevation and each one had a different average annual temperature. And they have measured, tagged, and ID'd the species of every tree in these plots. Okay, and so they had come up with, in this 22.5 acre plots, roughly 50 acres, over 1,000 species of trees. Okay, so in the entire Canadian boreal forest, which stretches over 1 billion acres, there are only about 20 species of tree. So here we see, in 50 acres, in an area roughly the size of, I think, like Fort Tryon Park, we're seeing 1,000 different species. So that just shows you that the tropics are where most species are. That pattern is repeated over most groups of organisms. And one of the characteristics of tropical species turns out to be that they have very narrow climatic ranges. So one of the things this guy said to me was, we're going down this ridge. He said, you're going to see like a leaf on the path with an interesting shape. Focus on that shape. Watch as we go down the path. You're only going to see that leaf for maybe 100 meters or so, because that's the whole range of the tree. This is the only place where it lives. And what they were looking at was, as the Andes warm, and the Andes are warming, very quickly, what are those trees doing? They can't move, obviously, but they can seed themselves at higher and higher elevations. And that's what's happening. You do see a lot of species on the move, but you also see a lot of species that are not on the move, that are just sitting there. So as the climate changes, these communities are going to clearly break down, and new ones will presumably form. And the question of what will happen to all of the organisms that depend, on what's there now, all of the birds and all the insects and all the mammals, is an open one. It's very hard, obviously, to track insects. They don't, they don't respond well to having these little tags nailed into them. But as the scientist Miles Silman pointed out to me, we're going to find out. We're in the process of finding out. We are running this experiment. We can only run it once, but we're running it, and we're going to find out the answers to that. So how else are we changing the world? Well, another very big effect of carbon dioxide emissions is the phenomenon known as ocean acidification. I suspect everyone in this room is pretty familiar with how that works, but I'll just give you the basics. And that is that the oceans have absorbed about a third of the CO2 we've put up so far. That comes to about 150 billion metric tons every hour. The oceans absorb another million metric tons of CO2. And the net result is that the acidity of the oceans has increased by 30%. So when CO2 dissolves in water, it forms an acid. That's just pretty basic chemistry. It's a weak acid. You drink it when you drink a Coke, but it's an acid. And we are changing the pH of the oceans very, very rapidly. And what the effects of that are going to be, are also not that easy to anticipate. Obviously, marine creatures only interact with their outside world through the water. But one thing that seems pretty clear is it's going to impact anything that has to build a shell or an external skeleton out of the mineral calcium carbonate. It really affects sort of the energetics of doing that. And lots of things do that. These are tiny little marine calcifiers called coccolithophores. You're seeing them under high magnification here. Common shellfish like clams are calcifiers, sea urchins, starfish, coral reefs. So lots and lots of marine organisms depend on the process of calcification. And one of the places, a couple of chapters in the book focus on marine organisms and how they will be affected. A lot of people trying to figure out, what the effects of ocean acidification are going to be. And this is a really interesting sort of natural experiment that I visited. Now, you're underwater here. We're in the Bay of Naples, in this area where there's a lot of volcanic activity, not too far actually from Mount Vesuvius. And it happens that there's CO2 bubbling out of the bottom of the sea there. And sort of naturally acidifying the waters. So I went out with a British marine scientist named Jason Hall Spencer, who had gotten this idea that if we looked at what happens near these volcanic vents, we sort of have a window into the future of the oceans. And what you're looking at here, I went with a National Geographic photographer, and he took this wonderful picture. And what you're looking at here is we're away from the vents. We're in a pretty ordinary Mediterranean community. You see, there's a sea urchin there. There's all sorts of this stiff seaweed, which is also calcified. There's calcifying seaweed. That pink smear of pink you see there, that's a tiny little algae that also calcifies. So you're seeing lots of different creatures there, different species there. And now we're moving near the vents. You see the CO2 bubbling out of the water, and you see what it looks like, that sort of lunar landscape. So this is when we get, pretty close to the vents. And in between, he, looked at every sort of possible pH between these two and came to the conclusion that at the pH that oceans are likely to reach, all of the oceans, by around 2100, if we continue to emit CO2 at our current rate, that about a third of the species in the Mediterranean drop out at that pH. They just can't keep up with it. So another way we're changing the planet, and this is just the last one I'm going to touch on today, is by moving species around the world. Everyone's familiar with this, with the problem of invasive species. I skipped over this. Coral reefs are a huge concern. Coral reefs are calcifiers. This is just a quote from some British marine scientists that it's likely that reefs will be the first major ecosystem in the modern era to become ecologically extinct, because corals turn out to be pretty sensitive, many species at least, to these changes in ocean pH. So back to our invaders. This is an Asian carp. He's been much in the news. Asian carp is actually several different species. They're incredibly voracious. They're filter feeders. They just eat through everything in the water column, have a terribly devastating effect on native fish. There's just a study that came out from the Army Corps of Engineers about what it would take to keep Asian carp, which are headed toward the Great Lakes, what would it take to keep them out of the Great Lakes? And the Army Corps of Engineers put a price tag of $18 billion on that one. These are zebra mussels. I don't know if people read the story in yesterday's Times. They're invaders from Eastern Europe. They're also voracious feeders, have done incredible damage, do commercial damage, stick to everything that they come in contact with, and really have devastated native mollusk populations. And there was a piece yesterday about a scientist who had was trying to find a biological agent, like a bacteria, in this case a bacteria, that could potentially fight zebra mussels. So we all have, if you have a backyard, you doubtless have plants in it that are not native species. Some people have pets that are not native species, but most of our non-native species these days are being moved around sort of unconsciously and inadvertently. And it's been estimated, for example, that 10,000 species are being moved every day around the world, just in ballast water. And this is another way that we're sort of running geological history backward and at a very high speed. So what you're looking at here is the configuration of the continents about 250 million years ago, when they all crashed together and formed one supercontinent, which has become known as Pangaea. And then they drifted apart owing to plate tectonics, and we got the world as we have it today. So all of these things have been evolving separately, right? The species in South America and Africa and India and Australia, have been evolving separately for tens of millions of years. And when we bring them all together, it has the effect of crashing those continents back together again. And you'll hear this phrase, you sometimes hear this phrase that biologists use, that we are creating the new Pangaea. And oftentimes this has no particular result when you bring species together that have been long separated, and sometimes it has sort of a not benign result, but no, not very dramatic result. They just sort of coexist. But every once in a while, you get really disastrous results. And when you think about it, if you're moving at least 10,000 species around the world every day, you don't need a very high proportion of those interactions to be disastrous before you have, quite a big problem. So this is actually the species that I begin the book with. So we've worked our way sort of from the end to the beginning. It's a Panamanian golden frog. It's a very beautiful animal, as you can see. It was considered a lucky symbol in Panama. It used to be printed on lottery tickets, which is rather ironic, because the golden frog, and really all frogs in Panama, started disappearing in the 1990s. And scientists eventually figured out, this is sometimes called the amphibian crisis, and it truly is a crisis. And scientists figured out that they were being killed by a fungal disease that had probably, almost certainly, been ferried around the world on frogs by people moving animals around the world. And one theory, which has not been proved, but one theory is that it was moved around the world on these frogs called African clawed frogs, which were used as early pregnancy tests. Because if you inject a female African clawed frog with the urine of a woman who's pregnant, she will lay eggs within a couple hours. So obstetricians actually used to have, tanks of these frogs in their office, and a lot of them were let go. You now have naturalized populations of African clawed frogs around the world. So one theory is that the fungus moved on African clawed frogs. And anyway, it was moving through Panama, and it was this interesting moment where people could actually watch it move. They actually could see the frogs disappearing, and they realized, or they hypothesized, that it was moving east, sort of along this, the way that the rivers move. And they decided to try to get a population of these particularly beautiful frogs and also some other species native to central Panama out of the rainforest and into some kind of protected facility. And they didn't have any place to put them. They went out and got the frogs, but they didn't have any place to put them initially. And so initially, the frogs literally had to be put up at a hotel. But then they built this facility. This is the El Valle Amphibian Conservation Center. You might be able to see some little golden frogs in those tanks. And this is one of the few places that golden frogs exist anymore. They're now extinct in the wild, like the Alala. There's some in zoos, and there's some at this conservation center. So this is, I'm gonna sort of wrap up at the beginning of the book. You could, in some ways, say, that this is a heartening story, like the Alala. It shows that people really are, concerned about other species. To use the words of Rachel Carson, that they care about what Carson called the problem of sharing our Earth with other creatures. And in the course of reporting the book, I did spend a lot of time, with people who have really devoted their lives to this problem. A lot of them are scientists, like the woman who was trying to get Kanoe to deliver. But a lot of them were also ordinary people. For example, at the El Valle Amphibian Conservation Center, I met volunteers who had come down from the States. They'd paid their own way. They were using their vacation days to help out because they wanted to help out. And obviously, even people who are not directly involved in conservation give a lot of money to groups like the World Wildlife Fund and the National Wildlife Federation, Defenders of Wildlife. The list goes on and on. And I'd like to sort of be able to end on that upbeat note. That if more of us just got involved in efforts like this, then that would be sufficient. But I'm going to be frank with you and say that's not really where I come out in the book. One of the central points of the book, really the central point of the book, is that our involvement, our caring is not really the issue. What's really the issue are the many ways in which we are changing the planet. And this is what makes us, comparable in our impacts to an asteroid. And unfortunately, unless and until we really confront that fact, the magnitude of the impacts that we're having, then I'm afraid we're not really fessing up to the problem. So thanks a lot. Howdy.
Hi. You showed a graph earlier. It was an animation where you showed the different parts of the world becoming warm and cold, and
Right.
it ended with the north part of the globe being very warm. Was that relative temperature?
That is off of a median that they choose some year. I can't remember exactly the year, but yes, everything is temperature deviation from this median.
Thanks. Hi.
Howdy.
So you talked about fossil fuel use. That seems to be the big issue, but there's also a lot happening in the world moving away from fossil fuels. So first of all, are there any other we do a lot of other stuff besides burn fuel.
Yeah.
So are there other?
But we burn a lot of fuel. Yeah.
But is that sort of a hopeful thing that we are starting to use more green energy?
It's a hopeful thing, but in terms of actual numbers, we can go back to we're using more renewable energy. We're also using more fossil fuels. I mean, if you just look at emissions trends, they're not leveling out worldwide. They have leveled out in the States, but worldwide they're actually tracking the very high end of. There are these scenarios which people may or may not be familiar with. The Intergovernmental Panel on Climate Change had these scenarios like, okay, this is what the future is going to look like. Here's a low emissions future. Here's a medium emissions future. Here's a high emissions future. We are tracking the high emissions future. Okay, so until that graph levels off. On some level, I don't want to say it doesn't matter if we're using more renewable. Obviously, it does. It's taking away from what that trend line would look like. But until we turn that around, we haven't really gotten a handle on this problem. So I do think it's very hopeful. Obviously, look, if we could convert our economy to not running on fossil fuels, that would be huge. That would be making an impact. That really would be. But I don't see signs that we're really on that kind of an actual transformative course yet. How's that? And I'm not alone. It's like not my pessimism. I don't think anyone sees signs of that at this point.
I know this was a short talk. You've talked a lot about the carbon cycle, but do you also talk in the book about nitrogen and some of the things that agriculture is doing?
I do not get into the nitrogen cycle, but I could have. I mean, one of the kind of interesting things, if you want to call it interesting, I don't know what the right adjective is, I could have chosen different ways in which we're changing the world on a planetary scale, and the nitrogen cycle could have been one of them. We fix more nitrogen. I don't know if people remember their high school bio once again, but you need to fix nitrogen. Plants can't use the nitrogen from the air because it's bound together in N2. So we need nitrogen fixing bacteria to transform nitrogen into a usable form. And when people figured out early in this century, a German chemist figured out how to take nitrogen from the air and convert it to ammonia and fix nitrogen. That was the beginning of nitrogen fertilizer. It's exactly a century ago, in fact. We just celebrated the century of nitrogen fertilizer. We now fix more nitrogen than all terrestrial ecosystems combined. That has huge, huge impacts, on living things. It's why for example, we have a dead zone every summer in the Gulf of Mexico because all of that fertilizer comes down the Mississippi River. It fertilizes the Gulf. You get these huge algae blooms. The algae dies. It drops to the bottom, and you have deoxygenated water. And dead zones are increasing worldwide, and it's all a function, of nitrogen fertilizer runoff. So that would be a whole other way, that we could have this conversation.
So speaking of agriculture, I read that even if we stopped using fossil fuels for power, the agriculture that we use to produce meat would still contribute like more than half of the greenhouse gases, but not carbon dioxide. Different ones, like, is that accurate?
I don't think so. How's that? I mean, our cows and things like that are burping methane, for example. That's one way that agriculture just produces CO2 without, actually burning fossil fuels. But I think maybe what you're referring to is, studies have shown that meat production in general, which is pretty fuel intensive and pretty crop intensive, obviously. And also has these other, effects of methane emissions. They are a major source of emissions. So, a lot of people, smart people, have sort of advocated that we all eat either a lot less meat or no meat, and that would have a significant impact on emissions. And I think it would. It's not going to eliminate the problem, but it would have an impact.
Hi, I'm wondering if you've encountered a lot of climate change deniers or human impact deniers, and if you have, what sort of arguments have swayed them?
Yeah. Well, climate change denial is such a weird sort of world, counterfactual world. Here's a graph showing you what's happening to CO2 levels in the atmosphere. And if you know CO2 is a greenhouse gas, which we've known for 150 years, and you're increasing it very rapidly and very radically, you'd say, okay, well, I kind of expect the world to warm up. So, we just have these ridiculous arguments like, it's cold in New York this week, so there can be no climate change. It's impossible. People much smarter people than I have spent a lot of time thinking, how can you counter, such, ridiculous arguments at this point? And it's very hard. I don't have the answer for that. But in terms of other human impacts, interestingly enough, you very rarely hear people saying, being ocean acidification deniers. It's just really, it's either too complicated or it's just irrefutable. You increase CO2 levels in the air. Very basic chemistry tells us you're going to be increasing carbon dioxide levels in the oceans. We can measure it. We are measuring it. The pH of the surface waters of the ocean is declining. It's pretty irrefutable, and once again the list goes on. We're obviously altering the nitrogen cycle. It's not really possible to deny that. So the weird way that we're sort of fixated on climate change, yes or no, I think is a complete function of a bunch of increasingly embattled disinformation sources, which have been funded, by all the usual suspects. I mean, all that is true that you read.
Hi, thanks for coming to speak with us today. That picture of the stark differences in what the ocean looks like is almost enough to make someone want to cry. And
it should be.
I think there are a lot of smart people who realize that change is happening, but it feels so impossible to make any change happen. And I guess my first question to you would be, what could change things? But I guess in thinking about my question to you, it's more a question of, do you think there's anything that'll change this trajectory, and what would that be? Because it feels almost like an insurmountable issue.
Well, I mean, yes, yes, it does feel that way. I think one of the reasons I'm glad to be here and talking to you folks at Google is because Google has been. There are very smart people at Google who are very aware of this problem and know what it takes to for transformative technologies to enter our world and really change the way we think about things and the way we do things. And I think that is one possibility. There is one possibility. I mean, some gentleman said before, there are renewable sources of energy out there that are increasingly being deployed, and that is true. Not in a transformative way at this point, but it seems to me not impossible that could happen. If very smart engineers like those at Google put their minds to it, it seems to me that is a possibility. I am not an engineer, so I don't claim to know what that's going to be, but there are very, very, very big forces at work here. There's 7.2 billion people on the planet. A lot of people, want to raise their standard of living, which unfortunately right now, tracks global GDP and global carbon, track each other. And unless, we uncouple those or decide, to have a lower GDP, we're in this cycle where emissions are just going to keep going up. Impacts are just going to keep increasing, and I certainly don't claim to have the answer of how we're going to break that connection or if we're going to break that connection, but it doesn't seem to me impossible that could happen.
Hi, I'm curious about the, besides for domesticated and invasive species, what kind of animals or species are benefiting from human impact? And is that change in scope or population count, is that a big effect relative to the first order effects of human impact? Or
that's a really good question, and I don't have a great answer for that. That it's a really interesting question. I mean, people have, for example, rats seem to do really well. All of the species that we know benefit from human disturbance. Seem to do really well. So rats have been taken around the world by people. They are now on islands like the Hawaiian Islands, where they never were. The Hawaiian Islands had no mammals. They're on really tiny, distant islands in the Alaskan, peninsula, where people never bothered to settle, but they left rats behind. So rats are everywhere. And one of the guys that I went out with in the book, a British geologist, sort of speculated, and it was tongue-in-cheek, but only half tongue-in-cheek, that rats will inherit the earth, that will be become sort of the dominant, group. But I think it is a really interesting question, because clearly, yes, ecospace that's being emptied, by other species may or may not be being taken up, by species that benefit from human disturbance. It's not clear that your total biomass is always going to remain constant. So I'm sure there are people doing interesting work on that, but I can't give you any great statistics on it. Clearly, also domesticated animals now make up a phenomenal proportion of the world's biomass.
Well, if there are no more questions, let's thank the speaker again.
Thanks a lot. Thank you.